So what we've got here is we'll look at our large overview of the nucleophilic addition and elimination. So first we've got the general pattern for the reaction, so we can go ahead and look at a mechanism. And when we start this off, we're taking a nucleophile. Typically we're looking at a strong nucleophile, but it doesn't have to be. And that nucleophile comes in, attacks the polar pi bond. That polar pi bond breaks, because that would be the weakest bond in the structure. You're looking at that pi system. That then ejects a lone pair of electrons up onto the oxygen, making it formally negative, and we now have that new carbon nucleophile bond. The next step of our mechanism would then be the electrons coming back down and now kicking out the best leaving group, which in this case we're going to show as leaving group, Lg negative. So at its core, really what we're doing is an addition followed by an elimination. In that, what is causing the addition? Well, it's a nucleophile, so we can call it a nucleophile addition. What gets ejected from the leaving group, or ejected from the structure, I know leaving group makes sense, but again, we want to kind of go back to our core or root definitions, and we're ejecting something with a negative charge. That best fits the definition of nucleophile. Because these types of reactions require some very particular patterns, okay? They require that polar pi bond and they require the presence of the leaving group. The amount of starting compounds that we can work from is fairly limited in scope, okay? So if we're, what the heck, come on. If we looked at our overall reaction, what we're trying to get at is actually two things in this statement, okay? First and foremost, we have this leaving group, and that is affecting the polarity of that polar pi bond. It's making that electrophile potentially more or less electrophilic than, say, another comparison. So by changing the leaving group, we can change the reactivity. So that would be a potential condition that we could do within it. The other condition that we could change would be that in this case, we're probably running under basic conditions because we see the formation of negative charge. Okay, could we run it under acidic conditions? How does that change the overall reaction? How does that change our mechanism? And so ultimately, all we're doing is taking all that same content that we had back in the previous unit, and we're now applying it to a particular special case of a polar pi bond, one that has a leaving group connected. That special case really boils down to these 5 main categories, and these might be useful to name. So we're looking at acyl halides. In this case, it's particular to chlorine, so it would be a chloride. We have acetic anhydride, the primary category being anhydrides. We then have our esters. Whoops. We have amides, and then we have carboxylates. For those people noting that the carboxylate looks an awful lot like a carboxylic acid and have noted that the carboxylic acid is not on this list, that's because the carboxylic acid is really kind of the parent of all of these. And if we were to look at where the carboxylic acid fell in this, its reactivity is closest to that of the ester. Okay, again, we're looking at what's that leaving group, what's that atom. In each of these cases, what we're trying to show is that we're really setting these up as these are now all of our leaving groups, and those are going to change the reactivity of our electrophilic carbon in each of those cases. Okay? Once you kind of acknowledge that, everything we do in this unit is just a repeat of the last unit. Okay? There really isn't a whole lot of new stuff to evaluate. There's some kind of interesting complications, but that's it. Like, that's all we do. Okay? So first thing I want to address is let's look at some thermodynamics and potential kinetics of these reactions. So if we were to go through and compare or not necessarily compare, but just look at, say, that ester converting across, what we'd be starting with is some energy for our reactant. We'd go to form an intermediate. That intermediate should be higher in energy because it's charged, and then we'd be going through to form the product. I got this question in the last unit. How do we decide where that product energy is? Well, it should for sure be lower in energy than the intermediate because it's neutral. Where it is with respect to the reactant has everything to do with the difference in energy of the most reactive things, which would be those leaving groups and nucleophiles. If we assume that our leaving group was more stable than our nucleophile, that means our product would be lower in energy. And now what we would do is just connect it out, and we've got our reaction, okay, or our energy diagram. One of the common kind of analyses that comes out of this, particularly as we add in other functional groups, is what explains the difference in reaction for each of those functional groups. And you'll very commonly hear people reference this comparison of leaving group and nucleophile. And the problem with that analysis is that that is happening in this second step. So when somebody says, oh, the leaving group is really good, that's why it's faster, what you're referencing is the activation barrier for that step, okay, that transition. Well, that transition is insanely small. If we look at the very first step, the transition or activation energy for that first step is much larger, and that's the rate limiting step. In that rate limiting step, we don't have a leaving group. So how can we explain the difference in reactivity for each of those individual species, okay, that we addressed? We've got the acyl chloride, the anhydride, the amide, and the carboxylate. Why is the acyl chloride reacting? Well, actually, before I answer that question, what do you guys think? Okay, would we expect the acyl chloride to react faster than, say, the ester? So if we were going to go through and make that comparison, and in this case, we don't really care what the nucleophile is, because it's going to be the same for both of these species. And our leaving group would be a G, that doesn't make any sense, would be chloride. Or if we went through and did it with the ester, and I'll fix the charge up above in just a second. So we're getting the same overall reaction, but what we're now trying to decide is which of these would occur faster, okay? That decision on why we care about faster has to do with what we're trying to do. If we're trying to get something to react so we can get out of the lab, then we want it to react as fast as possible without potentially exploding, okay? But how do we decide which one of these things is faster? As I said, the evaluation of the leaving group doesn't help because that's looking at that last step, which, as we saw in the energy diagram, was a very small activation barrier. Our rate limiting step is happening up here. So how do we know, or why would we be able to predict the speed of these relative to each other? Okay. Well, the crux of this is going to sit on the electrophilicity of this compound. One of those is more electrophilic than the other. Okay? If we go through to decide this, that decision ultimately comes back to everybody's favorite 5 rules: charge, size, electronegativity, all of which are going to be the same in this case. Okay? The atom that's reacting is that electrophilic carbon of the carbonyl, not charged, same size, same electronegativity. So we then move into resonance. Right? And if we looked at resonance, the oxygen can donate in, the chloride can donate in. Well, which one would be better at donating in? The oxygen would be better at donating its electrons in. If it's better at donating the electrons, what does it do to the electrophilic carbon? Well, it stabilizes it. That means that when we're looking at the reaction, the ester starts at a lower energy. In the acyl chloride, well, I already started writing it all out, so I'm going to have to deal with it. The acyl chloride is at a higher energy. What does that mean for our energy diagram? Well, again, we only care about that first step. If we look at our ester, we're going from here to our intermediate. That intermediate is the same for both. If we look at the acyl chloride, it's starting at a higher energy. The intermediate, again, same for both. The activation barrier for the red one, significantly smaller than the activation barrier for the purple one. So we can use the energy diagram based off of just charge, size, electronegativity, all that fun rules, and we can predict what would happen with the energy diagram. And sure enough, that is what we end up seeing. Okay? And so when we actually look at the energy diagram, that first step is definitely our rate limiting step, and that each of these species gets progressively more stable as we move down the sequence. So they were ordered nicely for you to kind of process this. Okay? And you should be able to go through and use charge, size, resonance, electronegativity, all that fun stuff. Charge, size, electronegativity, resonance, induction. You should be able to use those rankings to be able to explain the order that we see here. Okay? If you don't want to use the understanding behind it, that's okay. You do have to memorize it then. Okay? That's still more to memorize that I would argue you shouldn't have to do. Okay? So if we go through to actually look at rates of these, we sure enough do see these pretty big differences. The acyl chloride is reacting at a rate of 10 to the 11th. The anhydrides 10 to the 7th. The ester or the acid is at a rate of 1. Okay? 1 meaning it's an equilibrium. Okay? The product is not more or less stable than the starting material. Okay? So that's pretty incredibly slow. If we look at the chloride and the anhydride, those are incredibly fast. You'll note the aldehyde and the ketone have now shown up in this diagram. Okay? Those are important things to recognize because those are electrophilic carbons. That's what the whole last unit was about. We tend to not talk about them as much in this unit because they aren't acid derivatives. They don't have that good leaving group. Just because they don't have that leaving group doesn't change their reactivity in that scale. And if you remember to bring them into this argument, it can help you because now you can use all of that knowledge you have from the last unit and you're now just applying it to new structures, and that's it. Okay? So that reactivity has a lot to do with that starting material energy level. The higher in energy that starting material, the faster the reaction runs. Okay? The cheat behind this, if you will, we already kind of addressed, but I do have a slide here to show it, is that if we look at our overall reaction and we compare the nucleophile to the leaving group, okay? If your nucleophile is a larger negative than the leaving group, so, and by larger I mean more active negative, okay? The leaving group being more stable, our reaction is going to favor the more stable species. Okay, so we would expect the reaction to shift towards products. If the flip was true, we had a leaving group that was very, very reactive as a negative in comparison to our nucleophile, well, then we would expect no reaction. Our reactant should stay in place and it should never actually transition. So we can use this to help kind of cheat our way through it. It's not really a cheat, it's just an observation that works to explain, but is not valid scientifically. Okay? For those people being like, well, why do you ever talk about it? Do you still use Markovnikov as a name? That's the exact same explanation. Okay? Exact same issues going on with that. You're using archaic systems that we have better answers for. Okay? So if you want to use the cheat, you're welcome to it. Realize I will probably ask, explain the reactivity difference that is going to ask you to dig into the energy of your reactants and not that comparison between leaving group and nucleophile. Just a heads up. So, which then gets us to the slide that we showed earlier on, and I forgot to check if my picture's in the stupid way or not. This shows all of our interconversions. Note the acyl chloride's up at the very, very, very top because it's the most reactive. Okay? It is very easy to move down. Okay? This is why when you're going down a mountain, it's pretty easy. You just stop and you roll down the mountain. But if you try to just stop moving and roll up a mountain, it doesn't happen. Okay? So it's easier to roll down. And that's going to be the same case here. So that's why this order becomes so important, because it's showing that reactivity. We can move down the ladder very easily. And if we take a look at the acyl chloride can jump to pretty much any rung on the ladder depending on the starting material you're reacting it with. And that's kind of cool. The inverse is not true. Okay, so if I have the anhydride, let's go ahead and pick that really close to the acyl chloride. There's my anhydride. How do I get to the acyl chloride? Well, the reaction arrows here are intentionally not shown as equilibrium. If we move, I can't move that direction because the arrow very clearly shows that I can only go that way, which means the only place I can go is this direction, which takes me to the carboxylic acid. That's not what I wanted, so what do I now have to do? I now have to move upwards in a step 2 and use my thionyl chloride. Okay? So you have to kind of move through this carefully and recognize that our arrows are unidirectional because we can't jump up in energy easily. Okay? We reference that easily, you'll notice, well, thionyl chloride, how bad is that? Like, all we needed was one reagent. Thionyl chloride is exceptionally reactive. If you remember back in Unit 1, that off-gassed sulfur dioxide and hydrogen chloride gases. Those gases literally bubbled out of the solution, preventing the reverse reaction, okay, because those things aren't present anymore. So it's those kind of controls that allow our reactions to work and move neatly. What's nice about this is that we do, for the most part, only travel downwards. Of course, there are some kind of interesting things to note, as in 2 exceptions. One, we can move from that carboxylate up to the carboxylic acid. Note that that is a bidirectional arrow. We could either go up or we could go down. For those people being, oh my God, that's brand new. That's not brand new. That's literally just an acid-base reaction. Okay? That should be easy. Why are we able to transition so swiftly between those? You're adding a strong acid to force the reaction to occur. So those ones shouldn't be really new as an exception. What could be new as an exception is this interesting one of going from the amide to the acid, because that is moving up in the ladder, and all we're really doing is adding water, and that seems weird. Okay, water is not particularly reactive. Why on earth would we be able to make this transition? Okay, and this is where we would encounter the exception. It's not really an exception if we dig into the mechanism. Okay, so what I'd like you to do is pause for a second here and try and draw out the mechanism. I know we picked some awful structures for this overall drawing, so if you want to go through and abbreviate, okay, or just straight up delete things, because I'll probably end up deleting things, like do something like this, okay, that's cool. Go ahead and do that if that makes it easier for you to go through and draw. I picked the slide where it had all this on it, so I might very well just have to go through and do it. Okay, so again, please pause, draw out a complete mechanism. So do everything that you think you can to get to that product. Okay. The trick here is now I'm going to try and do this in my head. You should have had 1, 2, 3 steps. Okay. And so if you go back and look at your mechanism, you're probably saying, I only have 2. Okay, well, what happened? So let's go ahead and break this mechanism down and see what's going on. Okay, this is kind of a cheat out of the textbook, which is why they highlighted the active species here. Okay, why is all this here? That is there as a catalytic base. Can't act as a nucleophile because that is T-butoxide. That is not very nucleophilic, and that's not nucleophilic because I'm just going to stop there, sterics. Okay, so that's really just there to make sure we stay negative. The reactive species would be that hydroxide. I need to neutralize that hydroxide as a negative, which means I need to find a positive somewhere in my reaction. The most positive thing is going to be my electrophilic carbon. So I'm going to go ahead and have that attack. That's going to break my pi bond. Remember, we said the pi bond was the most reactive thing. And here's all the stupid drawings, because I said I was going to do it. There's our new bond to our OH. Here's that negative charge. Now what happens? We reform the pi bond and we kick out our leaving group, the leaving group in this case being that nitrogen, or that nitrogen structure, I guess I should say. Reformed pi bond. We'd have our OH, we'd have the nitrogen. Not sure if that was a 6-membered ring because that's how I'm drawing it. There's our lone pair. And for those of you that counted, you're like, well, here's the 2 steps. Don't I have the product? Well, no, we don't really have the product, okay? We might have the characteristic carboxylic acid, but we definitely don't have this other piece, okay? That seems a bit odd. So what happens at this stage? Okay, well, before we even get there, that nitrogen was your leaving group. If we compare that to our nucleophile of the hydroxide, OH minus versus N minus, which one was more stable? Right? Well, that's going to be a difference in electronegativity, right? Because charge, they're the same, size, same row, we don't worry about it. Electronegativity, oxygen is more electronegative. Because it is more electronegative, it will hold the electrons better, which means the nitrogen is a better nucleophile than the hydroxide, which means when we go back to our mechanism, that nitrogen attacks and we launch the reverse reaction. And if we look at this, those arrows that I just drew are probably not quite correct because they probably actually push very heavily backwards. So why does this reaction work? If we look at that yield, it's a 96% yield, okay? And that difference stems from the reactivity of that nitrogen. That nitrogen is very reactive as a nucleophile. Since it is negative, though, it is also a base. And as a base, what it could do would be deprotonate the carboxylic acid. When we go through and look at that result, we would now have, so for those of you counting, I also got the steps wrong. We talked about it a little bit earlier. We would now go through and have our nitrogen. I drew that color-coded wrong. With our hydrogen on it, and then our oxygen would have that negative charge. Okay, that reaction is a reaction between a carboxylic acid and the strong base nitrogen. That acid-base step is not in equilibrium. So while it may not be easy to transition from A to B to C, as soon as C forms, I go immediately to D. Because D is not reversible, we're looking at a constant equilibrium shuffling of A to B to C, and I'm constantly removing C, which means B has to replace the C, which means A has to replace B, and it now constantly shuffles across to get us to that final answer. Right? For those of you counting, that's not our final answer, and this also explains the presence of the step 2, the addition of H+. The addition of H+ is necessary so that I can finally protonate the carboxylic acid and get to that final answer. So all told, we're looking at 1, 2, 3, 4 steps. Okay, I think I said 3 earlier, but we're looking at a 4-step mechanism. So it's not so much that it's an exception, it's that we have to acknowledge that some of the products of this reaction can react with themselves in a non-equilibrium type fashion. What this means for us is that when we go through to look at an energy diagram, we've got the nucleophilic addition followed by the elimination, and we'd be like, well, damn, that's not going to work. Okay, and that's what this is trying to show with that energy difference. Reactant product, that's going up in energy. That's not a favored reaction. Okay, but if we advance ever so slightly with a small hint here, do you see what that hint was? Watch carefully. And back and forward. The reaction continues. And it's not so much just that it continues, it's that when it continues, it goes to form something that is exceptionally lower in energy. That massive drop in energy going from the amide not to the carboxylic acid, but the amide to the carboxylate, followed by an acid-base shift up. So it doesn't really break the pattern of what we saw on the ladder, because we are going down, we have to go to the carboxylate, but we end up forming intermediates that look suspiciously like we were going up. We aren't, we're actually going down. Okay, so just kind of interesting observations, and this is actually taken advantage of by Gabriel, and we end up with what is known as the Gabriel synthesis. Okay, Gabriel angels, for whatever reason, I see this phthalate or phthalimide and I think like angel wings. Right? And the reason the Gabriel synthesis is so cool, come to think of it, I haven't walked through this slide enough. I think it's going to reveal more than I want. Yeah, it's going to reveal a lot more than I want. Well, tough. Right? The reason the Gabriel synthesis is so cool is that when we look at this overall reaction, we might be thinking, well, dude, you just made a dicarboxylate. I actually don't care about that. That is actually utter trash. What I care about is this. Okay? The whole point of this reaction is that red box. Okay? That's the point and the kind of beauty behind the Gabriel synthesis, is that we end up making a primary amine. Okay? And for those of you thinking, well, didn't we make amines before? Well, sort of. Right? If we think about nitrogen as an amine, right? If there's our ethyl bromide, couldn't I have just mixed NH3 with the ethyl bromide to make that NH2? Wouldn't that be a primary amine? But what you should remember, back, it was supposed to be in Unit 1, but it shifted to the beginning of Unit 2, that nitrogen is now so nucleophilic that it reacts a second time. And we end up getting a cascade of reactions, primary, secondary, tertiary, and quaternary. Okay? So the nitrogen becomes so nucleophilic that we can't stop it easily. Here steps in Gabriel. And the point of the Gabriel synthesis is really all of that secondary junk out here is really just a control on the nitrogen. It is occupying those reactive sites, limiting its ability to act as a nucleophile. So if we go through the reactions, right, if we start this off, we're mixing it with a base, hydroxide, and at the very end we're like, isn't that mixing with a base also? We're actually mixing it with a nucleophile hydroxide there, and that may seem weird, okay, but we'll kind of address that. That base removes the hydrogen, which then gives us a nucleophilic nitrogen. That nucleophilic nitrogen can now do its substitution reaction. Right? The other lone pair on the nitrogen is occupied in resonance with the carbonyls, and so is not nucleophilic. So then what happens is we only get the single substitution. At that point, we can then add our KOH again, and this time there's no acidic hydrogens, So the KOH will act as a nucleophile instead and attack the electrophilic sites, right? Kicking off the nitrogen as a decent leaving group. And that's kind of the point of the Gabriel synthesis. Let's see. So yeah, there's that review if you remember that, right? That should look very familiar because we talked about that back in chapter, that says 20, but I think that's just a copy over. That initial sequence showed up back in chapter 10, I believe. And I don't have the mechanism drawn out for you. I think it's kind of neat. I know we're at 30 minutes, so if you're like, I don't need to see the mechanism, then go ahead and stop the video. If you want to look at the mechanism, then follow along. So let's go through and piece together this mechanism on how it cranks out. Right? And for those of you, again, being like, is you going to talk about more? No, this is literally it. I'm just going to do the mechanism. So if you want to piece out, that's fine. No judgments. Okay? You might miss some happy trees, you know, because I'm so good at drawing trees. Sorry. Our hydroxide acts as a base to start. We come in, we deprotonate. This gives us our first product. That nitrogen now has an extra lone pair. Okay? At this point, that's when we bring in the alkyl halide. For those people saying, well, why didn't we just use the alkyl halide at the beginning? Didn't we have that purple lone pair on the nitrogen to start with? Because remember, octets, we needed those. That lone pair is occupied in resonance with the carbonyls, and because of that is not nucleophilic. Okay? So we need to remove that hydrogen. Once the hydrogen's removed, we can now run our reaction. Sorry, there's lots of stuff to draw here. In this case, we had an ethyl, so there's 1, 2 carbons, and we have bromide chilling off on its own. We still have that remaining lone pair. And so again, for people saying, well, why can't it react a second time with a second equivalent of the bromide? That lone pair is occupied in resonance, and so is not nucleophilic. Okay? Which then means our reaction stalls at this point. There isn't anything, whoops, come on, that can react through. So what happens? We move on to step 3. Would have been nice if I'd numbered these right. This was step 2. This one was step 1. And remember, these are reagent steps, okay, not mechanistic steps necessarily. It just so happened that the reagent step and the mechanistic step matched. That negative hydroxide now really only has one thing it can attack, the carbonyls. We do a nucleophilic addition, breaking that pi bond. For those of you wondering, why did I pick that pi bond and not the other one? Doesn't matter. They're the same. So there's our new OH connected to the structure. We've got a negative charge on our oxygen. Those electrons can come back down, and we could now kick out that bad leaving group. So if we were looking at this, this is an equilibrium. That bad leaving group of our nitrogen, and it would now have, and I keep forgetting the lone pairs on the nitrogen. If you're doing your smart work, you got to watch out for that. It would have that negative charge. It could immediately pick up a hydrogen. Typically, intramolecular reactions are frowned upon, but this is an okay one because the distance between those is close enough and far enough, allowing for that to occur. So we'd have our O negative. We then have our neutral nitrogen with our hydrogen connected. We could now have a second equivalent of our hydroxide come in and attack break the pi bond, and we would effectively repeat that process again. And I'm kind of out of space, so I'm just going to say that we're going to repeat that process again. So that would be 1, 2, looks like 3 steps. 1, 2, 2, 3. And we would get to our final product. If we're going to break down our overall reactions, we have an acid-base reaction, followed by an SN2, because we're looking at backside attack, followed by a nucleophilic addition. I don't know why I switched colors there, and that kind of bothers me, so let's keep it constant. A nucleophilic addition, followed by the nucleophilic elimination, running out of space to write it in there. Our irreversible acid-base step, and then we started again with a new nucleophilic addition, nucleophilic elimination, and our irreversible acid-base step. Okay, so there's our whole Gabriel synthesis. Okay, kind of neat. We'll just kind of throw it out there, and we'll see if you guys come up with an interesting answer to it for Piazza. How do you feel that a green chemist would evaluate the Gabriel synthesis? Would this be a good reaction or a bad reaction? And with that, I'm going to go ahead and say I'm done. Thank you for watching all the way through that. It was very much appreciated. I hope you enjoyed it.